Okay, today we are going to discuss about the polarity of the feedback, meaning we need to decide is it a positive feedback or it's a negative feedback. Obviously, as we discussed earlier, we always aim to have a negative feedback except in some special applications like the oscillators, we look for the positive feedback. So let's see how can we decide the polarity of the feedback. And this is important thing to know. Okay, let's see the circuit. So we have a differential amplifier here with an active load. And we have the feedback through a resistor network. This is V out. Okay, so we want to identify is this a positive or a negative feedback. M2, M3, and M4. Now the procedure to do so is that you want to assume that there is a slight increase in the V input here. And then you want to follow on the circuit that what changes this increase in the input will cause into the circuit. If the behavior of the feedback helps or improves or supports this change that's going to happen on the circuit due to this increase in the input, we call the feedback as a positive feedback. While if increasing this input voltage and the changes that's going to happen here will be counteracted by the feedback behavior, then we will call it a negative feedback. Now we note that I want you to remember that if you have a common source here and you change the input, what's going to the output happen to the output here? And if we are applying the input here and we're taking the output from the source, what's going to happen? And if we are applying the input at the source, what's going to happen at the drain? This is a common source, as you know. This is a source follower and this is a common gate. So common source is an inverting amplifier. So if you increase the input, you expect that the drain will go down because of the negative sign. Source follower, if you increase the input, the output will also be increased. And in the common gate also is non-inverting, so increasing the input side will also increase the output side at the drain. So these are very important to know, otherwise you will mess up your calculation. So let's see what's going to happen, and let's do this with another color. So if I increase, I just missed the point here, 30, so go to add the active link. Okay, so if I increase this input voltage here, what I expect at this node here, according to what we did here, we expect that this node will go down. Okay, so this node we expect that it's going to go down. Now this node is similar to this node here, and it's similar to this any point here. So now this node has went down. What do we expect to see at this point here? Now we are applying the input at this gate and we are taking the output from the drain. We expect, this is again a common source, so we expect this point to go up because it's an inverting amplifier. Once this go up, this means that the out is going up because it's a similar node. Now once the out go up, what's going to happen to this node here? Since it's a voltage divider, it's also going to go up. Now, once this node goes up, what do we expect at this node here? Because this is again, we expect this node to go down. So you can see now, the increasing the input is forcing the V output to go up. while with the help of this feedback, we are forcing this node to go down. So we have a counteracting effect here. They are going in opposite direction. This means that this is a negative feedback. This is a negative feedback. Negative feedback. If it turns out that this is also a going up arrow, this means it's going to be a positive feedback. However, it's not the case here. Now let's take another example. Let's go the circuit here. So we have R, V1, we have Vn, we have RD2, and another common source amplifier here. This node is, we're calling it A. Okay, we have a resistive feedback here, RF1, RF2, and nodes are connected together, and here we have V out. Okay, now let's follow in this circuit what is going to happen. So assume again that our Vn goes up. Now this is a common source, so we expect this node to go down since it's an inverting amplifier. Now once this goes down, it's the same as this node here. So this input of this second common source stage is going down. So we expect the V output to go up. Now this V output is going up. Similarly, because this is just a voltage divider, we expect this node here to goes up. Now once this is going up, what is going to is we are entering a common gate stage. Now once this is going to go up, what do we expect here to happen? It's a common gate. Again, as we discussed, if this is goes up, this is will go up. So we expect this node to go up. You can see we have the feedback effect causing the node A to go up, while the change increasing Vn was wanting this node to go down. This two opposite effects, again, it's a negative feedback. Let's see one more example on this to make it easier to get the concept. So assume that this is RV1. We have a common source. The input is coming from a current now. IN, the input is a current, and we are having here another stage, and this is V out. Now the input here is a current, but let's assume that it's also there is some impedance here that we can convert to a nodal voltage here. So if we assume that the voltage node, the nodal voltage here is going up because of the input, what's going to happen here? Again, it's a common source amplifier, so this node will go down because it's an inverting stage. Now V out is going down, it's coming also here in the gate of this transistor. Now this is go down. What's going to happen here? Because it's a common source, it will go up. So again, let me repeat this. So assume initially in the orange color that the input is going up, this nodal voltage, due to its common source, the output is going down. The output is applied at the gate of this another common source stage. So it's going down the input. What's going to happen to the output that's measured here? It's going to go up. So you can see that those arrows, they are pointing in the same direction. This means the feedback has supported the effect of increasing the input, and therefore the feedback is a positive feedback. Okay, So now just let's take last example on this. Just for the circuit, we have here a current source, and we have here resistor VN, RS, another current source, and we have resistor VR. That's also applied on input here. Okay, now this is on and this is on top. Okay, let's see what's going to happen here if I increase the V input. If I increase Vn, again this nodal voltage is going to increase. Now where I go into the M2. Who's in the main amplifier? Is it M2 or is M1? Now obviously it's M1 because there is no amplifier where I apply the input on the drain of the amplifier. Either I apply it on the source or I apply it on the gate. So obviously M1 is in the feedback. The main or the forward path is M1 transistor. So the input goes in up here at the input of M1. What's going to happen at the output? Since it's a common source state, it will go down. Now the output goes down here. It's also coming here on the gate of M2. Now this is again another common source amplifier. So what's going to happen? If the input is going down, the output will go up. You can see now the two arrows are pointing in the same direction, which means it's a positive feedback. Let me repeat it one more time. So the input goes up. Again, this nodal voltage in the red goes up. The main amplifier M1 is going up the input. It's a common source, applying the input at the gate, taking it from the drain. So the output goes down. Now this output is also applied as an input of the feedback path, which is basically M2 amplifier. So the input goes down, the output will go up because this is also a common source stage. Since both arrows are in the same direction, this means it's a positive